In this video, we're going to connect our cell potential in volts to delta G, our chemical potential. And eventually we're going to come up with an equation we call the Nernst equation. In the last couple of chapters, we've defined some things that seem to be related to each other. We've defined E for these oxidation reduction reactions, and we've called that the electrical potential. In the previous chapter, we defined delta G, which we called the Gibbs free energy, but which is also called the chemical potential. And so it's reasonable to ask, is there a relationship between these two? And the answer is yes, there is, right? We can get a relationship that looks like this, that the delta G for an oxidation reduction reaction is equal to minus NF E. And often you see that F written as a script, right? Like a fancy F, right? And so, right, we've got our Gibbs free energy, right? We've got our electrical potential, check. This N is the number of moles of electrons transferred in the balanced oxidation reduction reaction, right? And F, whether written this way or as a fancy script, and often you see it in print as a fancy script, is, we've seen this before, that is Faraday's constant, which is that 96,485 coulombs of charge per mole of electrons. Okay? So that relates units of delta G and units of E, which are in volts, right? This is in joules, this is in volts. And remember, right, the negative charge is important because we said when delta G is negative, reactions are spontaneous. But when the potential for an oxidation reaction is positive, the reaction is spontaneous. So a positive potential times that negative charge leads to a negative delta G. So that keeps our trends consistent. So this relationship is important. So let's consider these two reactions, right? Iron plus iron, or ferric ions, iron 3 ions plus 3 electrons going to iron metal. Nickel 2 ions plus 2 electrons going to nickel metal. Here's the standard reduction potentials, right? Now clearly we can't have two reduction reactions. We have to take the more negative one and reverse it in order to get a reasonable reaction. So I will write that down. So here we've rewritten this, right? Iron is still written in the reduction direction, right? The iron reaction. But the nickel now is being oxidized, which turns a negative potential into a positive one. And when we add those two together, we get a positive potential of plus 0.194 volts. But what we haven't done is balance this. And notice, right, we're in a situation we dealt with when we were balancing oxidation reduction reactions, right? The number of electrons gained has to equal the number of electrons lost, right? And so we've got 3 and 2. The least common multiple is 6. So that means we have to multiply everything in the first reaction by 2 and everything in the second reaction by 3. And so when we balance this, we get 2 ferric ions plus 3 nickel atoms, or 3 moles of nickel if we're going mole to mole, give 2 moles of iron and 3 moles of nickel ions. But what's important to us here is this and this. What was transferred is 6 moles of electrons, right? That becomes our N in our equation. So if we want to calculate the delta G, right, our delta G, since this is an E0, right, this is a delta G0, it's going to be minus N F E0, which is going to be equal to minus 6 moles of electrons, right? There's our N, 96,485 coulombs of charge per mole of electrons. That gets us in coulombs. And then our E0 is 0.194 volts. And remember, a volt is equal to a joule per coulomb of charge. So that cancels that coulomb unit, and we end up with joules as our unit, and we get an answer of about negative 112,300 joules with a little rounding. Okay? So, if we know the cell potential, we can find the delta G. Conversely, if we know the delta G for an oxidation-reduction reaction, we can find the cell potential. But remember, we have to know what the balanced equation is and what that number of electrons is in that balanced equation. Let's consider these two reduction potentials, right? These are standard reduction potentials for the vanadium ion and the nickel ion, right? And so let's write out our expression, right? The vanadium one is more negative, so that one will have to then become the oxidation half reaction. So if we write this out, let's go with our oxidation first. So we'll take vanadium and have it be oxidized to our vanadium ions plus 3 electrons. And the potential for that would then be plus 0.255 volts. And then we'll do our reduction of our nickel. Right, so our nickel ions plus 2 electrons going to nickel metal. That would stay at minus 0.23 volts. Right? And so we're going to end up then with a potential of plus 0.025 volts. All right, so let's go back to one of our equations we dealt with in the previous chapter. That is, the delta G0 for a reaction is equal to minus RT times the natural log of the equilibrium constant, right? But we also found, right, we just introduced that a delta G is equal to negative the number of moles of electrons times Faraday's constant times the cell potential. Well, if we make the standard cell potential and delta G0, now we've come up with another relationship here, right? That our minus NF E0 is equal to RT times the natural log of our equilibrium constant. And if we isolate E0 on the left side, then we end up that our E is equal to, keep our negative sign in there, right? Make sure we write this down right. If we have negative RT over minus NF, right, then our negative signs cancel. This is where the eraser can be handy, right? Erase that one, erase that one. Times the natural log of the equilibrium constant. And here we have another expression relating our standard cell potential to our equilibrium constant, the same way we could relate delta G to our equilibrium constant. And so now, right, if that is E0 for that cell, the standard cell potential, we can find the equilibrium constant by substituting this in here and remembering, right, our stoichiometry. If we balance this, right, we've got 3 and 2. When we balance that, it's going to be 6 moles of electrons again when we properly balance those two. So our N will be 6. So we substitute in and solve for the equilibrium constant. So here is our properly balanced equation for the reaction between vanadium and nickel ions to make nickel and vanadium ions. Here's that standard potential we calculated, and here's the equation we just came up with, right? And so we can substitute in and solve, right? That our 0.025 volts is it going to be equal to R, which is 8.314 joules per mole Kelvin, 298.15 Kelvin, right? We're under standard conditions, 25 degrees Celsius. Our N is 6 moles of electrons in our balanced equation, and our Faraday's constant is 96,485 coulombs of charge per mole, and all that is times the natural log of the equilibrium constant. And if we solve for that, right, if we go through and do that math, we get that the natural log of the equilibrium constant is 5.839, and therefore, right, the equilibrium constant is e to the 5.839, which is about 343, right? So we can find the equilibrium constant. And conversely, right, if we knew the equilibrium constant for a process, right, and we knew how many moles of electrons were transferred in that process, we could use that to find the standard potential in a straightforward way, right? So now we've dealt with this equation under standard conditions. Just like with delta G, now we have to look at the potential to work with it in non-standard conditions. All right, so if we look at our other major equation, right, our more complex equation, our delta G is equal to delta G0 plus RT times the natural log of Q, right? And so right here we go, right, if we know that delta G is equal to minus NFE, and delta G0 is equal to minus NFE0, And we can substitute those in, right? We get minus NFE equals minus NFE0 plus RT times the natural log of Q, right, for our reaction. Well, if we divide by this minus NF, we divide this by minus NF, which means we have to divide this by minus NF, we get this, that the cell potential under non-standard conditions is equal to the standard cell potential minus RT over NF times the natural log of Q. Right? And this version of this equation is called the Nernst equation. After a German scientist. Okay? So now we have a new relationship giving us the potential under non-standard conditions. If we know the potential under standard conditions, we know how many moles of electrons are transferred in the balanced reaction, and we know the reaction quotient for the reaction. So let's look at our reaction again, right? Our vanadium-nickel reaction that we've been using, right? So if we try to write an expression for Q here, right? We've got nickel solid. Its activity is going to be 1. And so all we have on the product side that we can put in really is our concentration of vanadium ions squared. And if we look on our reactant side, vanadium is a solid. And so all we really have is our concentration of nickel ions cubed, right? That would be the Q for our reaction, okay? So let's imagine that we set up a couple of electrochemical cells like we've been talking about, right? Where we have, right, our vanadium on the oxidation side and our nickel on the reduction side. We've got our salt bridge, right? We've got those connected, right? And we've got them in solution, right? If we had 1 molar vanadium ions in here and 1 molar nickel ions in here, our potential would be this, right? But let's say instead of having that, let's put in 2 molar vanadium ions and 0.1 molar nickel ions. How does that change our potential, right? Well, we just found out that, right, our potential is equal to E0 minus RT over NF times the natural log of Q, right? And Q here is going to be equal to the concentration of vanadium ions in that cell, which is 2 molar squared, divided by the concentration of nickel, which is 0.1 molar cubed. And so if we do that math, we get a Q of 4,000, right? And so now we can substitute in, right? So we get that our overall potential under non-standard conditions is going to be equal to our E0, which is plus 0.025 volts, right, minus R, which is 8.314 joules per mole Kelvin, times 298.15 Kelvin, divided by N, which is our 6 moles of electrons, right, in our balanced equation, and F, which is our 96,485 coulombs per mole of electrons. And that's all times the natural log of 4,000, right? So if we work that out, we get that our standard potential is equal to our plus 0.025 volts minus 0.036 volts, which is going to equal negative 0.011 volts. And so under these conditions, our reaction becomes unfavorable. Instead of going in the direction we have it written, right, it will tend to go back in that direction under these conditions, right? So we have found a potential under non-standard conditions. So these are a couple of equations that are important. We should be able to solve for anything that's in there, given anything else, right? If everything else is given, you should be able to solve for any of these variables, right? The potential under non-standard conditions, the potential under standard conditions. You need to be able to find the appropriate number of moles and the Q, right? And you need to be able to find the proper form of Q given the balanced equation, right? So, right, this is another set of equations that are important to electrochemistry.